Hello, good morning, everyone. Okay, so let's get started with today's lecture. Okay, so today we are going to be talking about this concept called concurrency. All right, and we are going to be understanding how a multi-threaded program can actually manage its threads, its resources, while being concurrent. Okay, so if you remember last week's lab and as well as the lecture, okay, we have seen that in a multi-threaded environment, things are very dynamic, right? So you create multiple threads, and any point of time, context switching can occur, and we also have the round robin behavior, okay, as we saw last week, right? So things are very dynamic. Okay, so any point of time, one thread can be running, and you can switch over to another thread, and so on. Okay, so and at the same time, there'll be many resources that are also shared among different threads. So how do you manage these resources? How do you provide some way of synchronizing their usage or controlling their usage? All right, so these are some of the things we're going to be looking at in today's lecture. All right, and then as usual, we will look at the lab for this week. Okay, after we're done with the material. Okay, so let me share screen. Okay, and then we can get started. Okay, can everybody see my screen that I'm sharing? Okay, thank you. All right, so this is the lecture topic. So if you last batch of students, actually this was what you call scheduling policy was run first, and then concurrency was done. Okay, but this time around I decided to switch it around a bit so that we can make sure the lab part is not affected. All right, and then the scheduling lecture we will have it next week. Okay, so before we go into the details, okay, again, this is the again a quick recap of the challenge. Okay, so your final challenge has two challenges. The challenge one, all right, I think you have seen, if you have not seen the videos, go and see some of the videos okay, on the website. All right, later I'll share the link as well. Okay, so you can look at all the videos submitted by your previous batch students to sort of see how the competition run was done. Okay, so so this part is actually where Uncle Jalil's office is. Okay, so it's somewhere over here. So this is where the office is. Okay, Uncle Jalil's office here. Okay, and so this is where the starting point is, where we have the two tables. So this is the table where once you come in through the door, you see it on the left hand side. All right, so that is where we will start. Okay, and when we go, when you control your robot, you will have to first go up and down a ramp. Okay, and after you go up and down the ramp, there will be a cone. Okay, so you're supposed to go around the cone. Okay, go around as in this way. Okay, and then once you are done, okay, you have to go through the two cones at the side here, and then for this other cone again you have to go around the cone. Okay, and then you go straight, then there's another ramp. Okay, then over here there's two cones, so you just need to maneuver through them. Okay, so one way is you can just go this way, okay, and then sort of go straight to the finishing line over here. So the starting and ending point is the same. All right, so that is basically the route. Okay, so I'm very sure there will be some students who don't watch this video, okay, and don't know what is happening. And then what will happen is it has always happened where they will do the competition run and then they will do it wrongly, and then one attempt is wasted. Okay, so please make sure you understand the sequence very well, because if you do it wrongly, okay, you don't get a additional chance. All right, so you're only given 2 attempts per challenge. Okay, so make sure you understand the sequence well and you try it out, or you have enough practice so you know what's happening. Okay, so for challenge 1, okay, you are operating it in the remote control mode. That means you are actually controlling it, so you have full sort of control over how the robot is going to behave. So you need to practice. Okay, so in your team, okay, whoever is confident to do it should go ahead to practice and design the user interface, on how you want the robot to behave. Correct. So as long as you are confident with controlling your robot, then you should not have an issue with completing this challenge. Okay. So the killer part is actually the RAM. Okay, why is it the killer part? Because many a times, okay, many robots will go and then commit suicide. All right. Why I say literally commit suicide in some cases, because sometimes when it drops off, okay, because you do not secure your components or things like that, what happens when it drops off? Suddenly your wires get loose, your components fall off and things like that. Okay, and your timer is still running. Okay, your timer is still running. So you need to quickly put back the things and then start again from here. All right, so that is why I keep telling you all to try and make sure that you secure everything correctly. If you want to design some casing for your board, go ahead and do it. Okay, try to make sure everything is secure and safe. Okay, in the event that it topples, there is minimal damage and you can quickly carry on again. All right, so that is again up to you. All right, till the end there will always be students who still don't quite arrange your wires and components properly, and then once it drops off and some wire comes out, that's it, you're lost. Okay, in that panic mode, you do not know what wire came out from where. Okay, then one attempt again is gone. Okay, so these RAMs, we have them in the DSA lab. All right, starting from this week, I will ask Uncle Jalil to place them out. All right, so those of you who already have your robot up and running, you can try to maneuver and see how it works. Okay, so again, you need practice, okay, to make sure you understand how your robot is going to behave on this terrain. Okay, for the challenge 2, okay, is in autonomous mode or self-driving mode, okay, where you are going to be putting your robot inside a sort of a grid, and your obstacle, okay, is basically look back at the project specification. Is basically the 4 toilet rolls that I mentioned, okay, that you need to rearrange, you need to tape up, okay, and you are free to cover up in whatever surface that you like. Okay, it's up to you. Okay, so if you want to cover it up with the white paper, black paper, gold paper, anything, okay, it's up to you how you want to cover up this sort of square, okay, as the obstacle. So you can choose whatever material that sort of works well with your code. All right, and what you're not supposed to do is just put it there, okay, and your robot is supposed to go straight, okay, and once it detects it, it's supposed to go around and then come back. Okay, so when it comes back to this point, okay, you can use anything to stop it. I mean, in a sense that you must still stop based on the sensor. Okay, so this must still be based on the sensor. Okay, based on your sensor, your ultrasonic sensor or IR sensor, whatever that you use. Okay, but you can choose any object to place here. Okay, so if you want to put a book, you want to put anything, okay, but it must stop based on the sensor. It was not crash and stop. Okay, it must stop based on the sensor, okay, within this space. All right, so in the grading criteria, okay, we will have some penalty. Okay, if let's say your robot does not fully stop within the grid, okay, maybe partially it stops, okay, part of the grids are stopped, then there is some penalty marks and so on. Okay, so to stop it, you must again place some object to trigger the sensor, but you can choose any object you like. All right, that is to stop the robot once it comes back to the grid over here. Okay, so you can decide how you want to do this. Okay, now the important things are this, that you are not allowed to hard code the distance to stop it. Okay, so just to confirm this, okay, just to confirm that you have not done any hard coding, okay, we will do a test before you do challenge 2. That means we will just check whether your robot is able to detect an obstacle that is placed at some random distance. Okay, so this is just to do a verification that you have not done any hard coding to your robot, okay, based on the distance. Okay, if your verification fails, then automatically you get 0 marks for challenge 2. Okay, so you need to make sure that given any random distance from 90 to 150, your robot can still detect and perform going around the obstacle. Okay, and then once we have verified that, then you can go ahead to do the actual challenge. Now you are given $40 budget per team. Okay, so this one I already clarified in the earlier lecture. Initially, I said $50, but I went to check back again. It's actually $40 per team. All right, so you can purchase any additional components you want to fulfill the challenge run 2. Okay, so again, up to you, okay, how you want to do it. But again, this is the budget you have. Okay, so you need to purchase, and then at the end of the semester, I will tell you all how to proceed with the claims. Okay, so the claims are not so fast. Okay, so you need to be a bit patient. All right, so just buy what is really necessary. Okay, to do this. Okay, now this is very important. The integration of the sensor of obstacle detection must only be done using the KL25Z. All right, that means you cannot integrate any sensor, okay, to do this onto your ESP32. Okay, whatever that you want to connect, okay, everything must only be done through the KL25Z. All right, so this is again an important point, all right, for your challenge run 2. Okay, so again, please make sure you are catching up with the work, okay, in terms of the hardware and the integration of the components, all right, so that over the next 2 weeks or so, more or less, the main RTOS components will be covering. And once that is done, you can actually put everything together from all the things you have developed in the first half and actually complete the whole project already. All right, so it's important that your hardware is ready, okay, so that once the RTOS parts are complete, it becomes a lot easier to just put everything together and start testing your robot. Okay, so now let's so that was just to recap on the project. Okay, make sure that you understand, all right, the details of how it's going to happen. All right, and as I mentioned before, the challenge will be on the last week of the semester. All right, which means you do not have any lab access time on that week. All right, so you need to make sure everything is done before the final week. All right, and that will is important. Okay, so you do not drag it all the way to the very end. Okay, so let's get started with the actual lecture. Okay, so this lecture, like I said, is on concurrency. So what is the concept? All right, so in terms of hardware, okay, when you talk about CPUs or GPUs and different types of hardware architectures that people have designed, so how have we tried to provide some concurrency or parallel processing in the hardware sense? Okay, so the most basic one is this, correct? A single instruction, a single data stream. Okay, like how we learn how a basic processor works. Okay, you fetch an instruction from memory, okay, in the processing unit, then you fetch some relevant data, then you process it, and then you can write back the data or so on. All right. The next variation to this is multiple instruction but single data. That means I can take one piece of data and send it to 2 different instructions at the same time. Okay, so that is one way of designing hardware, okay, to achieve some sort of parallel processing. The other one is single instruction, okay, with multiple data. Okay, that means I take the same instruction that I want to execute, but I can send different data units, okay, to the same instruction at the same time. Okay, so I need multiple processing units to do this. Okay, and of course the most high end would be multiple instructions and multiple data all happening at the same time. Okay, so when you talk about let's say multi-core architecture, okay, that is effectively what you're trying to aim at. Correct, that means you have so many cores and all of them are able to execute different instructions with different data at the same time. Okay, so the hardware sense is actually very easy. Okay, to design a hardware for this is actually not so challenging. The more challenging part is how your software is going to be able to optimize to make full use of this hardware resources that you have. All right, so to give you an example, okay, so let's just say that I have a piece of code. Okay, I write a piece of code. Again, I say this is 1,000 lines of code. All right, can I just say that I break it up into 250 lines each and send it to one processing unit each? Okay, it's not so easy, correct? It's not so straightforward because when you write code, there is always a lot of dependency, okay, between the execution, the variables, and so on. So it's not so straightforward to just say that my compiler will just compile and split the code and just randomly allocate to different units. Okay, it's not so straightforward. You need to look at how the dependency plays a part. Okay, and there's no point splitting into multiple units if eventually this block has to wait for this block and this block has to wait for this block. Then eventually it still comes back to the same thing. Correct. So the idea of parallel processing at the hardware level is quite challenging. Okay, because you need to think of how the code is supposed to be split across multiple units, but at the same time, they can still run in parallel without having too much of dependency on each other. Okay, so there is a lot of challenges involved if you try to do this at the hardware level. Okay, so these are the hardware sort of architectures available. All right, and I think if you there'll be some modules that you might be doing, okay, where you will go more in depth into the HDL, hardware description language, okay, VHDL and Verilog, where you will learn how to actually write code that will translate into a processor architecture design. Okay, then you probably go into more details about all this stuff. Okay, so the other way is where we use the operating system, okay, to actually provide this parallel processing concept. Okay, and it can work on a single processor without any issue. All right, and with a single processor, okay, you have easier memory and data management, and you have a consistent scheduling policy. Okay, so whichever scheduling policy you choose, you can apply it throughout the entire system that you're going to design. All right, so that is basically the focus of what we are looking at. Now, in terms of single-threaded and multi-threaded, okay, what is the issue? Okay, if I say that I have a variable over here, okay, and I write a function, okay, so you a thread or a function that has some code that accesses this memory. All right, now when I access this memory, I know that this particular function that is currently accessing this variable is the only one doing it. Okay, but of course, in the embedded system context, you also have the other issue, which is the interrupt. Okay, so if an interrupt also tries to access this variable, then you have an issue. All right, but that is probably the only thing that you need to be careful about in a single-threaded environment. Okay, whether interrupts are also going to access the same variable that your main function is trying to access. Okay, but in a multi-threaded context, that issue is magnified. Okay, because now all the threads, okay, task 1, task 2, everybody can try to access this same resource. Okay, so when we say memory, it can be a memory that has a value. It could be a resource. Okay, like on our board, the RGB LED. Okay, it's a single resource. Okay, the single LED, and I can have multiple tasks all trying to control the LED at the same time. Okay, so what is going to happen? So these are the challenges we need to be aware of. All right, so this leads us to one tricky issue, which is basically what we call a race condition. Okay, where different processors access a shared resource. Okay, and they perform some computation, and the result of the computation actually depends on the exact way in which the processors interleave. All right, so this is actually a tricky situation, because when we say it's a race condition, that means it is something that's sort of dependent on how it sort of executes at that particular point of time. All right, and why I say it's a very tricky issue is because it is a problem that only occurs or may only occur occasionally. Okay, when you are developing a system, all right, the best problem to have is a problem that happens all the time. Okay, why I say that? Because when you have a problem, okay, or some bug that happens all the time, that means it's consistent. Okay, it consistently fails. So if it consistently fails, it's easy to run some tests, debug, and figure out what is the cause of the issue. Okay, the most challenging problem is the one that happens once a while. Okay, because you don't know when it's going to happen the next time. Okay, so it's very difficult to capture it. All right, so this kind of race condition issue is very challenging because you don't know when it's going to happen. All right, and when you say shared resources, like I said, it could be some memory, it could be some shared objects or resources. Okay, and it sort of depends on the sequence of operations, okay, that your multiple threads go through. Okay, so let's look at this example over here where I have a variable k. Okay, so this is a global variable, okay, and I have a function increment k that is going to increment k by 1. Okay, so both function A and function B both call increment k, and both function A and function B are tied to through two different threads. Okay, so this is like a task A or thread A, and this is task B. Okay, so two different threads running, and both of them are going to call the same function, which is increment k. All right. Now, in a real world situation, correct, we must understand that k equals to k plus 1, okay, is not something that can be executed in a single indivisible step. Okay, so indivisible, it's not invisible. Okay, indivisible step. Okay, so when we say atomic operation, means that it's an operation that cannot an atomic operation is one that can complete in a single cycle. All right, but k equals to k plus 1 is a non-atomic operation. That means it cannot be completed in a single cycle when you're talking about a RISC system. Okay, so RISC stands for reduced instruction set computer, okay, which is basically the architecture that ARM uses. All right, so in a RISC-based system, okay, k equals to k plus 1 is non-atomic. Okay, it cannot be done in a single step. Okay, why? Because when you compile this code and you look at the assembly language or the assembly conversion, you will see something like this. Okay, where the first step here is to load, because k is where? K is some variable in memory. Okay, some variable in memory. So the processor cannot directly operate on a memory. So if I want to manipulate some variable in memory, I need to first take this data and put it into an internal register, maybe R0, R1, R2, something like that. So that is what we call the load instruction. So you need to do a load from memory. Now the second step is where I can do whatever operation I want. All right, so I need to do the add operation. Okay, so I use the ALU to do the add operation, and then I get the result. Okay, so usually the result is also stored back in some register. Okay, could be the same register, could be some other register, doesn't matter. Okay, so that is the second step. And then the last step is to do a write back. That's what we call the store operation. Okay, so a single line in C, all right, can easily translate into these 3 lines in assembly language. All right, so that is where the challenges come in when you talk about concurrent system. If this was a single threaded system, then no major issue. Okay, because in a single threaded system, I know I will go in this sequence. Okay, 1, 2, 3, and so on. Okay, but in a concurrent system, there are issues. Okay, so let's see what happens. Okay, so in a single threaded system, again, you only have a single task. Okay, so the CPU one here, you can think of it as just task 1 or thread 1, where I run this code. So I load the value, increment, and store back into memory. Okay, now let's look at it in the case of 2 tasks. Okay, so here it says CPU cost, but you can just think of it as 2 tasks. Okay, so you can think of this as task 1 and task 2. Okay, the same idea, where I have both of them. Okay, like what we saw in the example code just now, 2 tasks running the same code. Now let's see if I were to run both of these tasks correct concurrently. If my initial value is k, then of course I expect the final value to be 2. Okay, if both of them have finished execution. All right, so of course that is only possible if this happens. Okay, I complete task 1 and then I complete task 2. Okay, or I complete task 2 and then I complete task 1. Okay, so these 2 possible scenarios will make sure I get the correct result, because when I complete task 1, the value of k will be 1, and here k will be 2. same thing. When I complete task 2, k will be 1, k will be 2. Okay, each task increments k by 1. Okay, so that is basically the sequence shown here. Alright, so either way, you get the correct answer in the end. Now, what if there is a context switch in the middle of one of the tasks? So I take task 1, I load the current value, I do this, I increment the value. Okay, so right now inside register R1, the value is now 1. Okay, initially k is 0. Okay, initially k is 0. But after increment inside register R1, the value is now 1. But before I can write back, there is a context switch here. Okay, a context switch happens, and then task 2 runs. So when task 2 runs, what happens? It takes the current value of k, which is 0, correct, and does a load. So what happens? It increments into R2. So what is R2 now? R2 is also 1. Okay, in step 2. And then I switch back again. Another context switch. Okay. Sorry, here is here I write back. So when I write back here, what happens? Okay, when I write back here, what happens is your k becomes 1. All right. So the third step here is I write back and k becomes 1, and then I do a context switch here. Okay, when I do a context switch here, what happens? The current value of R1 is also updated to k. So k still becomes 1 again. So both the tasks have completed, but my final k value is only 1. Okay, so that is an issue over here. Okay, that's the issue over here, because I would have expected the k value to become 2, all right, but now it has become 1. All right, even though I have run the increment function 2 times. All right, so again, this is just one scenario. Okay, this is another scenario where I load again, and then after I load into R1, task 2 runs. So task 2 completes, and then task 1 carries on. So in both cases, what happens? Here k equals to 0, and over here your k becomes 1. But over here again, your k still remains 1, because this is another register. This is your R1 register that is updating the k value. Okay, so you can see that this is a issue, correct? This is a real problem, because we expected the k to have incremented twice, but you only see it incrementing by 1. And again, this is very tricky because the context switching is very dynamic. Okay, in some cases when you run the code, maybe there is no issue at all. Okay, everything seems perfectly fine, and then suddenly because of some other dynamics in the program, suddenly there is a context switch, and then this issue happens. Okay, so it's very difficult to catch because it happens, or it may happen randomly. All right, so results are incorrect only sometimes. So this is the main issue here. Okay, it's not consistent. All right, and it depends on the timing relationship, okay, between the various processes. All right, so how can we eliminate this race condition? Okay, how do you deal with this? Okay, so that is where the idea of a critical section comes in. Okay, that means, what is a critical section? Okay, a critical section is basically a region of code where we access shared resources. Okay, that means if there's some part of the code where I'm going to get access to some resource, okay, which is shared with another task, then that section of the code becomes what we call a critical section. So if I go back here, okay, in this example, the part of the code that accesses k. All right, so in your actual task 1 and task 2, you may do a lot of things. Okay, but since k is a shared variable, all right, whenever I access k, that part of the code becomes what we call a critical section of the code. All right, so how can I protect this critical section? All right, so the OS itself actually has a very good built-in mechanism, which we call Mutex. Okay, and Mutex basically stands for mutual exclusion. Okay, so in mutual exclusion, basically what happens is you are able to lock the access to a particular resource, okay, once you take the mutex that is tied to that resource. Okay, and once you lock it, okay, which means that you are the only person who is able to access it. All right, and with that, okay, you can sort of ensure you have this exclusive access, okay, to use that particular resource. All right, so one thing about mutex is it is enforced by the OS itself. Okay, so when you try to access a resource, okay, and you're not able to acquire the mutex, then your OS will take the necessary action, okay, on that particular task. Okay, we will look at that in a while. All right, and of course, that means that if you need this resource but you cannot get it, then you are of course delayed, okay, until you are able to get that resource. Okay, but you only delayed for a finite amount of time, which is the amount of time that somebody else is holding on to that resource. All right, okay, so we will look at that in a while, and we also talk about what we call deadlock, okay, later on. Okay, so let's look at this idea here. Now, let's say now I have thread A and thread B, okay, and both of them right now try to access this increment K function. Okay, so what I need to do is inside my code. Okay, so inside my code, okay, whenever I have the function called increment K, what I must do is before I access this shared resource, I must say Mutex Lock. Okay, and after I finish, I must say Mutex release. Okay, so what will happen? Okay, so let's assume that task A runs first. So this is the first task to run. Okay, and once task A runs, it says Mutex Lock. So when I say Mutex Lock, that means I am acquiring the lock. That means I'm saying that I'm the one who is going to use this resource now. Nobody else should use the resource. Correct. So if nobody else should use the resource, okay, and let's assume that after I do the Mutex Lock, there is a context switch that happens. Okay, as we saw, context switch can happen just through round robin itself. Okay, so if let's say thread A and thread B are both in the same priority, then at any point of time after I lock the mutex, okay, even before I have run increment K, I can actually have a context switch. Now, when I have a context switch to thread B and thread B runs, okay, so thread B also wants to do the same thing. So task A and task B have the same code. Okay, they both have both want to call increment K, and both must do a mutex lock before and mutex release after. So when mutex B, when task B tries to do a mutex lock, what happens? Okay, the OS will know that task A already locked the mutex. Okay, so all this is actually managed with the OS. All right, so the OS already knows that task A, okay, already locked the mutex. So since task A has already locked the mutex, when another task, in this case task B, tries to do the same thing, it will not allow it to happen. All right, so the OS does this management for us. So the OS will say that, okay, task A is already using the mutex, okay, so task B is not allowed to get it. So in this case, all right, what is going to happen is you will put task B into a block state. Okay, it will put task B into a block state. So this is again managed by the OS. So once task B goes to a block state, what will happen? It will allow a immediate context switch back to task A. And task A can run. Okay, task A can run and do whatever it wants with the shared resource. So it can call increment K 1 time, 10 times, 100 times, doesn't matter. So it can do whatever it wants with the resource it has already locked. Okay, task B has no choice but to wait. Correct? It will be in a block state, it will be waiting until a point of time when the task A finally decides, okay, I am done with the resource. I want to release it for somebody else to use it. Okay, then it calls mutex release. Okay, when it calls mutex release, what happens? Okay, the OS gets notified that the mutex that was currently causing task B to be blocked is now available. Okay, so what will happen at this point of time is the OS will automatically unblock task B. When task B gets unblocked, which state will it go to? Can anybody tell me? Which state will task B go to once it gets unblocked? Correct, it will go to ready state. Okay, when you unblock, you will transition to the ready state. Okay, so that is what the OS will do. Then, of course, transitioning to the run is managed by the scheduler. Okay, because you do not know who else is ready. Correct, maybe there's another higher priority task that is already running, or that just also became ready. So the scheduler may switch to that task first. All right, so we do not know when it will go to run, but what we know is when task A releases the mutex, task B will acquire the mutex, okay, and it will come out of the block state and go to the ready state. Okay, then the scheduler will decide when it goes to the run state. Okay, so the whole idea of mutex is you provide this mutual exclusion. That means you are sort of locking this access to a resource, and only when you release that resource, somebody else can take over and run, okay, with that resource. Okay, so in terms of coding, is fairly only a few functions. So first you create a mutex ID, there's a global sort of variable. Then you create a new mutex, okay, with OS mutex new. Okay, and then you can acquire and release based on these two functions here. Okay, so there's a question: what if multiple threads want to take the mutex at the same time? Okay, so when multiple threads want to take it, okay, it all depends on the sequence of who asked for it first. Okay, so the sequence of whoever asked for it first will determine the order in which the mutex will be allocated. All right, so later we will look at some examples, okay, to understand how this thing works a bit better, okay, in the lab. All right, so these are the few functions, all right, for mutex. Okay, so even though it's fairly straightforward, it can also cause a lot of problems, okay, if you do not manage it well. All right, so when you learn all these tools, okay, that the OS provides us, okay, the important thing to understand is these are tools to help us make better use of the OS. All right, now if these tools you do not use it properly, okay, or you use them in a wrong way, then what will happen is you may end up creating more trouble for yourself, okay, because you have used these tools wrongly. Okay, so I will show you later, okay, a demo on what are the things that can go wrong, okay, with mutex, which is also a common issue that you might face in your project. Okay, now let's look at another similar sort of mechanism that the OS provides. All right, and that is called semaphore. Okay, so the idea of a semaphore is a bit similar, okay, to mutex. Only thing is semaphores have a number of tokens. Okay, so in the mutex concept, when I lock the mutex, okay, that means I am accessing this shared resource. All right, then once I release, then somebody else can take. All right, whereas in the semaphore context, you can have a few resources that could be shared among different tasks at the same time. All right, and then I use semaphore as a mechanism to allocate or deallocate these resources. All right, so what you need to do is before you access the shared object, you need to take the semaphore. All right, so you need to take. Now you can only take the semaphore if the number is greater than 0. Okay, so maybe I come back here first, but I say number of tokens, number of resources. So what is the example? Okay, so take a simple example. Let's assume that you have your KL25Z. Okay, let's assume that right now I have 3 PWM channels. PWM1, PWM2, and PWM3. Okay, so we have more, but let's assume that we only have 3 PWM channels. So right now I can say that these 3 PWM channels are my resources. All right, and I can have maybe 5 tasks. Okay, all of them need PWM. Okay, I have 5 tasks, all of them need PWM, but I only have 3 PWM channels in my controller. Correct, and I cannot do I do not want to do any pre-allocation. Correct, I want the task to get the PWM only when it needs it. All right, so this is an example of how you can use semaphores in your code. That means I can create a semaphore, okay, for PWM, okay, and I can put an initial value of 3. All right, so if let's say now task 4 is the first one to say I want PWM, okay, then I will say, okay, I allocate 1 PWM to task 4 and so on. All right, so you are able to allocate resources as and when they are available. So when task 4 finish, it give back the count go back to 3. All right, or if after that task 3 asks, then it go back to 1. Okay, then task 2 also asks, then go to 0. So when it goes to 0, then there are no more resources. So when task 5 or task 1 try to ask for a semaphore and the count is 0, then that is where the OS does the management. That means it will say that, okay, now one of these tasks is asking for a PWM, but there are no more PWM blocks available. So it must go to a block state until one of these earlier tasks that acquired it, okay, task 2, task 3, or task 4 releases the semaphore. Okay, then I can allocate to whoever is waiting. All right, so that is an example of how you can use the semaphore concept. Okay, that means I have a limited number of resources that needs to be shared among many different tasks. All right, so the idea is I must always take the semaphore first, but I can only take if it's initially greater than 0. Okay, if it is greater than 0 means the resource is available, so I can take it, I can decrement the value, okay, and I can return and carry on. But if it is 0, that means there are no longer these resources available. Then what I need to do, I need to block the process. All right, so that is basically what happens when you try to take a semaphore. If it's available, I take it and I carry on. If it's not available, then the OS will put it to a block state. Okay, now once I have finished, okay, I can return the semaphore. Okay, once when I return the semaphore, I will increment the value by 1. Okay, now if the queue, okay, the queue is the queue of, okay, of who is waiting. Okay, who is waiting for the semaphore? So if there's nobody waiting for a semaphore, when I return the resource, okay, the semaphore will just increment by 1. But if there's somebody already in the queue waiting for the semaphore, then I will automatically unblock that task that is waiting and allocate the semaphore to that task. Okay, and move it to the ready state. Okay, so let's look at what is happening, okay, with this example. Yeah. So if we look at this here, what happened is initially, okay, I said I got 3 resources, and so P is to take. So the concept of P is to Sam take. Okay, and B is Sam give. All right, so let's say now a task takes 1 resource, so the remaining is 3 becomes 2, and then another task takes the resource, then becomes 1, and then the earlier task is done with the resource, so it releases the resource, so it goes back to 2. Okay, so whenever a task is done with the resource, okay, and there's nobody in the queue, so automatically when you release the semaphore, it increments the count. Then another task comes in, it takes another resource, so it becomes 1. Then one more task takes and it becomes 0. Now at this point of time, what has happened is I no longer have any resource, any semaphores available. Okay, that means all the resources have been fully used up. So at this point of time, okay, if process X comes in and tries to take a semaphore, it is not able to acquire it. So what will happen is it will join the queue. So it is waiting for a semaphore to become available. Okay, waiting for semaphore to become available. And another task also comes in, process Y, and the task also tries to acquire, and again it gets blocked. Okay, because it is not available. So again, it is put in the queue. All right, when one of the tasks releases the semaphore, what happens? You can see that the number does not change. Okay, the number still remains 0 because it is equivalent to saying that I tried to give back, but the moment I give back, it straight away gets allocated to whoever is in the queue. Correct. So what I will do is I will unblock process X. So X will be unblocked and it will be removed from the queue. Okay. Then again, another task gives back. So again, because there is already somebody in the queue, the count does not change. Okay, I will unblock that task that is in the queue and I will just keep the count at 0. Then when the other tasks start to give back, then I will slowly increment again. All right, so that is the concept of how a semaphore will work. Okay, so in terms of semaphore, the routines are similar. You first need to create a semaphore called OS semaphore new. Okay, and then there is a maximum count and initial count. All right, so this one we will look at it when we look at the lab. Okay, and then to take the semaphore is OS semaphore acquire, and then OS semaphore release is to give back. All right, so all these OS related sort of APIs that we are using can be different across different OS. Okay, so for RTX, okay, we use these terms. Okay, if later on you try to learn another OS for another project or so on, the concepts are still the same. All right, only thing is their syntax will be slightly different. So they may call it OS SAMTake. Okay, and here they may call it OS SAMGIF. Okay, so the concepts are the same. They may just use different names, okay, for those OS-based functions. Okay, so now that we have looked at both Mutex and Semaphore, what is the sort of overlap or similarity in a sense? Okay, so one of the advantage of Semaphore is you can use it also for signaling from task to task or ISR to task. Okay, so what you can do is you can say that, okay, which you will actually do in the lab, okay, not this week's lab, next week's lab, where you can actually have ISR, okay, and you can have a task. Okay, so you can have a task, maybe it runs, okay, it runs to some point here, okay, and then it waits. Okay, yeah, so there could be a case, for example, where you have a task that is running, okay, but you do not want the task to finish everything. At some point of time, you want to wait for some event, okay, to happen, and maybe that event is triggered by an interrupt. Okay, so what an interrupt can do is when the interrupt is triggered, okay, it can actually pose a semaphore. Okay, and the task could have been waiting for a semaphore. All right, so by designing a mechanism this way, what you can do is a task can be waiting for some trigger which will come in through the ISR. And when the ISR sends that semaphore over, the task can now unblock and carry on, okay, from where it left off. Okay, so that is one sort of example of where you can use semaphores, all right, in a sort of way to synchronize between multiple tasks. Okay, so you can have you can extend this idea to even task to task and so on. Okay, so for example, task 2 is running. Okay, but when task 2 is running, at some point of time, it has to wait because it needs task 1 to have completed something. Okay, or task 3 to have completed something. So it can wait until maybe task 1 does something and then it posts a semaphore. Then it can carry on. Then it wait again, maybe for task 3 to finish something. So when task 3 finishes something, it posts another semaphore. Then it can carry on. All right. So this is a mechanism that can actually be used to sort of provide some synchronization between tasks. Okay. So even though we design the multitasking architecture such that every task runs by itself, you also can provide some synchronization, okay, between different tasks. Okay. So a task can wait for something else to happen before it starts to carry on to the next step. All right. Okay, Mutex, okay, we generally don't use it for this kind of signaling or whatever between tasks. We use it exclusively just to make sure that you provide protection to a shared resource. All right. Now, the idea of this protection can also happen with semaphore, right? Because in the semaphore context, if I try to take a semaphore and the current value is 0, then it will also get blocked. All right. So a binary semaphore, in a sense, can have some similar behavior. That means I create a semaphore with a value of only 1, initial value of 1. Okay, so it's only 1 or 0. So it becomes similar to that mutex, correct? Available or not available. Okay, but there is a difference because in mutex actually there is this other feature called priority inheritance. Okay, this one we'll cover at a later time, but Mutex has this built-in sort of enhancement, which is priority inheritance, which is actually very, very important, okay, when it comes to using shared resources. Okay, but this concept we'll cover in another lecture. All right, so even though we may at the surface level think that they are the same, actually there is some difference. All right, okay, so common pitfall. Okay, semaphore handles several copies of equivalent resources, whereas Mutex handles one. All right, so this again, this concept is, I mean, it's a bit maybe misleading. All right, because when you say semaphore, yes, we have multiple resources that you can control. Mutex is not meant to handle a situation where you have a lot of resources and you're trying to allocate. Mutex is used in the context of providing protection to a shared resource. Okay, so when I have a shared resource and I want to make sure that when this task is executing or using this shared resource, nobody else should use it, then I use Mutex. Okay, but when I have multiple resources, okay, you want to use semaphore as a way to manage that. All right. And another thing is semaphore does not keep track of the order of access. So it treats all resources identically. All right. So in the earlier example just now, when I said you have 5 tasks with 3 PWM, it treats all the resources identically. That means it does not differentiate the 3 PWM blocks that are available. It treats all of them identically. So whoever asks for it will get access to whichever resource is available. All right. So that is sort of the common understanding between Mutex and semaphore. All right, so what is a deadlock? Okay, so a deadlock is where you have processes waiting for others to finish. Okay, so the all the resources can be released. Okay, so for example, okay, I have task 1 and I have task 2. Okay, and let's say both of them, okay, have a shared resource. Okay, both of them have a shared resource, R1 and R2. Okay, so both of them require R1 and R2, okay, to function. So let's assume the task 1 is running first and it acquires resource 1. Okay, and then it's running, and then halfway there's a context switch here. and task 2 runs, and task 2 runs, it acquires resource 2. Okay, and then it runs. Okay, and then before it finishes, there's another context switch, and task 1 tries to acquire resource 2. What happened? It's not allowed, so it'll go to a block state. Okay, so let's assume that there's a context switch back here, and now task 2 runs and it tries to acquire resource 1. Now what happened? It's also not allowed, correct? Because resource 1 was already acquired earlier, so it becomes blocked. So what happens? In the end, both of them become blocked forever, correct? Because task 1 is waiting for a resource that task 2 has, and task 2 is waiting for a resource that task 1 has, and both of them need each other's resource to finish up their code or finish up their function. All right, so you can see that in a situation like this, okay, this is one potential issue with Mutex. Correct. That means if you have a task 1 and task 2, okay, and both of them require exclusive access to R1 and R2, okay, but because this context switching happens, okay, and then these resources get blocked by each other, then at the end nobody runs to completion. All right, so this is a potential issue, okay, that can happen if you do not manage this well. All right, so how can we sort of prevent this from happening? All right, or what is the solution to this? Okay, so one of the so this is basically the condition for the deadlock. Okay, like what I said, where you have resources, okay, holding, and you hold one while you request for another. Okay, and you also use the mutex so that nobody else can get access to it. All right, so this is again another example, okay, where you have a circular wait or dependency, all right, to different resources by different processes. Okay, so these are all the kind of conditions where a deadlock may occur. All right, so to sort of prevent this, okay, so sort of prevent this, what you can do is, okay, one possible way is, you can say is acquire, okay, resources in same order. Okay, so what do you mean by that? That means if task 1 and task 2 both require resource 1 and resource 2, then I must acquire them in that same order. Okay, so if I were to redraw this again, then what will happen? So task 1 will run, it will require resource 1 first. Okay, so if there's a context switch and task 2 runs, it must also try to acquire resource 1 first, so it'll get blocked. Okay, so which means that task 1 can carry on, acquire resource 2 and finish. When it finishes, then it can release R1 and R2. Then both of them can be allocated to T2 to carry on. All right, so that is one very simple way that at the software side we can do. Okay, where you have shared resources, you ensure that everybody acquires resources in the same order. All right, so in the event where there are shared resources, the moment the first task acquires the first resource, it will sort of ensure that it will get the rest of the resources and run to completion. Then only another task can come in to acquire those resources. All right, so this is one way of doing it. Okay, of course, advanced software tools are also available where they may also scan your code to actually preemptively tell you of possible deadlock situations, okay, that can occur in your code. All right, so that is again one of the issues with Mutex that we need to be careful about. Okay, so let me just mention a few points, okay, from what I observed last Friday when I came to the lab. Okay, so the first thing is the IP address. Okay, so the static IP doesn't always seem to work, okay, for some of you. All right, so even though it is, it may work at home, okay, but when you go to the lab and you try to run it again, it says connected, but then it's actually having another IP address. All right, so if you do not want to use the static IP, one way is you just let it boot up and show the IP address, and inside your user interface, you have a text field, okay, where you can just key in the IP address the moment it boots up, and subsequently you just append all your commands to the IP address and send it out. Okay, so whether it's forward, reverse, stop, or whatever, you just append that string to the IP address and you can send it out, okay, over the network. Right. The next thing is the interrupt. Okay, when you want to configure interrupt, okay, your KL25Z is only receiving the data packets. Okay, it's not sending out anything. So you only need to enable the receive interrupt. Okay, do not enable the transmit interrupt. Okay, why? Because when you enable transmit interrupt, what happens is the moment your transmit data register is empty, it will immediately trigger the interrupt, which means you're going to be continuously getting triggered by the UART interrupt because your transmit data register is always empty. You're not sending anything out. Okay, so that sort of hogs the interrupt. Okay, and you are not able to capture the incoming data. All right, so do not enable the TIE. Okay, only enable the RIE. Okay, when you are trying out the UART interrupt code. Okay, and the last thing is the UI design. Okay, so I mentioned this before. All right, the UI design is totally up to you. Okay, using the app, okay, whether you want to use Android or iOS is only a suggestion. Okay, you don't even have to use an app if you don't want to. Okay, you can design it as a web interface also. Okay, so if you want, okay, because your ESP32 is actually running a web server. Okay, so you can actually run your user interface directly from the ESP32. Okay, and just let it boot up and show the user interface at the IP address it connects to. Okay, so it's up to you to decide how you want the user interface to be designed. Okay, app, web interface, anything is up to you. Okay, because now you are just dealing with IP addresses. So any way that you want to send this information across is up to you. Okay, as long as you feel comfortable, okay, that you can use it effectively to control your robot, then that is good enough. Okay, so any interface is totally up to you to decide. All right, so these are a few things that I wanted to just bring up, okay, based on my observation last Friday. Okay, so let's go for a break now. Okay, now it's about 10:05. We'll go for a 10 minutes break. 10:50 we'll come back, and then I'll just run through the lab, okay, on the Mutex, so we understand what is happening. All right, so let's go for 10 minutes break. I'll see you all back here at 10:15. Okay, so for the lab manual this week, there's two parts to it. The first part is on the priority. Okay, so that part I'll let you all do on your own. Okay, basically is to configure different tasks or different priority just to see the behavior. And the second part is on the Mutex. All right, so let me focus on that. All right, so for Mutex, all right, as what we mentioned, the first thing you need to do is you need to create a global Mutex ID. All right, so I call this my Mutex over here. Okay, and after that, inside your main, you must call OS Mutex new. Okay, you must only call this after you have initialized the kernel. Okay, so after you call OS kernel initialize, then you can call OS Mutex new, okay, to create a new Mutex. Okay, so after you have created a new Mutex, okay, I have now created both the threads LED red thread and green thread as before. Now, if you look at both my code for LED red thread and LED green thread, basically what is happening is the code for controlling the LED is the same. Okay, code for controlling LED is the same. Only thing is now, since I treat the RGB LED as a shared resource, right? It is shared by both tasks. I want to make sure that I have exclusive access to the LED, to the resource. I control it, then I release the resource. Okay, same thing I do for the green thread. I acquire, control it, and then I release it. Okay, so let's see what will happen. Okay, so before we look at what happens, let's have a poll to see your opinion on this. So what do you think will happen once I run the code? Okay, so if you look back at the code, basically you have the same two tasks. Only thing is I have done a mutex acquire and release before I control both the LEDs. Okay, I think most of you believe you'll be red first, blinking, then green, and then you repeat from the beginning. Okay, so a small percentage believe that it could be both together. All right. So let's see. Okay, let's see what happens. Okay, so let me clear this. All right, so let me come back to our code here, and at the same time, let's bring out our camera. Okay, so let's run this. So red, green, red, green, and so on. Okay, so let's so even though that is correct, most of you got it correct, but before we move on, I think it's important to understand what is actually happening. All right, because if you take it at face value, you might still get the wrong understanding of what is happening. Okay, so let's understand what is really happening here. So I have the LED red right here, and I have the LED green. Okay, so both of these stars are there. So we know that LED red thread was created first, all right, and then it will run. So once it runs, what does it do? It takes the mutex. Okay, so it will take mutex acquire. So it will take the mutex. All right, so once it takes the mutex, it says that it has exclusive access to the resource, and then it carries on. Okay, and then it switches on the, so it on the LED. Now after it on the LED, you know it goes for some delay. Okay, delay for 1 second. Okay, and because of the nature of the context switch, all right, the round robin, we know that at some point of time here, okay, you will have a context switch. Okay, so of course the delay itself will trigger a context switch, okay, because it goes to a block state. Now when that happens, okay, we have a context switch here. So LED green, okay, was basically all this while in the ready state. It was waiting for a chance to run. Okay, and once the delay was called, all right, it goes into a context switch over here. So when it goes to a context switch, what will it do? Okay, so the first thing it tries to do in the code is it tries to call mutex acquire. Okay, but the mutex was already taken by the LED red. Okay, so when it tries to take a mutex acquire, the OS will say that it is not available, all right? Okay, because it is already taken. So it will go to a block state. Okay, so it will stay in a block state. Okay, until a point of time when the delay is finished. Okay, so this 1 second delay is finished by the LED red task. then it comes back, it off the LED, okay, and then it will release the mutex. Now when it release the mutex, okay, what happens? This would, at this point of time, okay, we know that it goes to a ready state. The task B, which was currently blocked, will be unblocked and it will transition to a ready state. Okay, now at this point of time, what happened? The task B is ready and this one is still running. Task A is still running. So after it releases the mutex, what will it do? It tries to go back to the beginning of the code. So in the beginning of the code, what will it do? Again, the beginning of the code, okay, after it releases, it goes back to try to acquire the mutex again. Correct? So it will try to acquire mutex. But since the mutex was already allocated to task B, okay, this will now go to a block state. All right, and that will also allow the task A. All right, so we do not know exactly when task B might run. Okay, task B, because of the round robin nature, okay, it could also be that even before this happened, okay, task B already run. Okay, it could be that it already run somewhere here. Okay, we do not know. Okay, but what we know is when task B runs, it will already have acquired the mutex. So when it has acquired the mutex, at that point of time, it can go ahead to on the LED. All right, when task A gets a chance to run and it tries to acquire the mutex, it will see that the mutex was already taken, so it will go to a block state. Okay, so this process will keep repeating. So when task B has the mutex, it will on, it will go to the delay. Okay, or 1 second. Okay, after the 1 second finish, it will come out, it will off. Okay, it will off the LED and then it will release. Okay, it will release the mutex. Only when it releases the mutex, it will allow the task A, okay, which was currently blocked, to unblock and go to a ready state. Okay, so now it is task A's red LED task turn to control the LED. Okay, so that is basically what is happening. All right, so this background switching of the task, okay, how the mutex acquire sort of allows a task to go from the block state, okay, and then eventually becomes unblocked. So that is the important understanding you must have. Okay, that this is all happening in the background. Okay, the OS is managing it for us. So whenever a task has already acquired a mutex and another task is trying to get it, you automatically go to a block state. Okay, but once that mutex is now available, it will unblock. Okay, and then based on the scheduler policy, it will then get a chance to run. All right, so that is basically what is happening, okay, in this first example that we just saw here. Okay, so I think this is when red releases the mutex, it is still ready state. Okay, when red releases the mutex, it is still running. Okay, at this point of time, it is still in the run state. Okay, only if round robin occurs or it runs to acquire mutex, then it will go to a block state. Okay, so that's why I draw this line over here, because if it happens to be that there is a contact switch after the release mutex has occurred, then task green LED may already get a chance to run and switch on. Okay, but if there is no contact switch, then when the loop repeats and red LED tries to do another acquire mutex, then it goes to block state, then the contact switch might happen here. Give me a minute, huh? Okay, so that is basically the most basic behavior, correct? That means both of them acquire and release. Okay, so the question, why would red fail to acquire the mutex on the second round? Okay, the red will fail to acquire the mutex on the second round, okay, because it already tried to acquire the mutex in the very beginning, okay, at this point here, okay, when there was a contact switch. So since it already tried to acquire the mutex in the very beginning, it is already blocked and waiting for the mutex. So the moment the mutex is released, okay, by the first by the red LED, the OS will automatically allocate it to the green LED. Okay, because the green LED task is now in the queue waiting for the mutex. Okay, so that is again okay, so this is the correct way of using mutex. Okay, that means we know that the LED is a shared resource, okay, between the two different tasks, and so I ensure that the red LED or the task that want to control the LED follow the rules, which is take the mutex first, control my resource, and release the mutex. Same thing I do here. Take the mutex, control the resource, and release the mutex. Okay, so now let's make some changes. Okay, so now it's going to get a bit more interesting. Okay, so now we're going to see what happens when you try to play around and use it in some funny way. Okay, now let's assume that now what I'm going to do is the red LED thread is going to follow the rules. Okay, the rules say I acquire the mutex, control the LED, and I release the mutex. But the green LED thread is not going to follow the rules. That means it is not going to take the mutex or release the mutex. Okay, only the red LED thread is going to do it. Okay, but the green LED thread is not going to take or use the mutex in any way. All right, so let's build the code and let's get your opinions. What do you think will happen? So only the red LED is taking the mutex and releasing the mutex. Okay, so the green LED is not. Okay, so I'm using the mutex at all. Okay, so got only a small response so far. Okay, so now let's move ahead. Okay, so majority of you have chosen this, which is red and green on, red and green off. Okay, whereas a small number have chosen red first, then green, and then only red repeats. Okay, so let's clear this and try to look at what is going to happen. Huh? Okay, so I'm going to debug. Okay, so let's run this. Okay, so it's quite bright. Okay, well, basically you can see it's yellow. Correct. That means it is red and green together. Okay, at the same time. Okay, so now this is leading to another very important concept. Okay, an understanding of mutex. Okay, so if you see this, what is happening is both of them are actually controlling the LED, even though only red is the one acquiring and releasing the mutex, whereas green is not acquiring or releasing the mutex. Okay, so this concept is very important, that the mutex is a OS based sort of feature. Okay, the idea that the mutex is tied to some resource, is tied to some hardware or whatever, is only in the programmer's mind. That means you as a programmer, only you know why you created the mutex. The OS does not know why you created the mutex. Okay, all the OS does is it follows the rules of how that particular object is supposed to be used. So as far as the OS is concerned, if you create a mutex, you can acquire it, you can release it. If you try to acquire, it is available, then it will allow you to carry on. Okay, if you try to acquire but it's not available, you will go to a block state. All right, so that is basically the rules of those are the rules of the OS, correct? So in our case, what has happened is the LED red thread has followed the rules, but the LED green thread did not. But that is not the issue of the OS, correct? Because the OS does not know why you created this my mutex. Okay, so this is a classic example of something that can go wrong when the code does not follow the rules. Okay, because when you created a mutex or this mutex, the idea was you are using it to control access to a shared resource, which is the LED. Okay, but one person used it correctly, the other person did not. Okay, and this is, like I mentioned, a common mistake that can happen, especially with shared code. Okay, because when you and your friends are working together and one of you follows these rules correctly, but another person maybe is not aware, okay, that a mutex was created to control the LED or control the PWM or something, and then the other person goes ahead to just access that resource without locking the mutex, then things will go messy. All right, so this is where you need to be very careful that if you are having a mutex or something to control your resources, access to your resources, everybody should follow the same rule. Okay, then the behavior will be correct. Okay, if not, the behavior will be different from what you expect. All right, so that is the first rule, okay, of things that can go wrong if you do not use it correctly. Okay, now let's do one more change to this. Okay, so LED red thread is again having both acquire and release, but LED green thread is only going to acquire, but it's not going to release. Okay, red thread is doing it correctly. Green thread acquired but forgot to release. Okay, so what is going to happen? Okay, so let's think about it. Okay, and you can put your opinions here. So let me repeat, only the red LED thread is acquiring and releasing the mutex. The green LED thread is only acquiring, but it does not release the mutex. Okay, so majority then in the option of red first, then green, and then green continuously repeats on after that. Okay, 20% of you feel that is great, then green, and after that there's nothing. Okay, so okay, let's leave this first. Okay, and let's see what happens. Okay, so this is the change. Red is both acquire and release. Green is acquire but do not release. All right, so let me build the code. Debug. Okay, so let's see what happens, huh? So red, green, and nothing else after that. Okay, so let me rewrite it again. Red first, green, and then no activity after that. Okay, so why this behavior? Okay, so why this behavior? So let's come back to analyze it. All right, so what has happened is the first time was correct. Okay, LED red acquired the mutex, you switch it on. Then the LED green tag acquired the mutex. Okay, so that part is fine. Then the green also went ahead. Okay, but over here what happened? The green did not release the mutex. Okay, so the green LED thread acquired the mutex, switch it on, switch it off, but it did not release the mutex. Okay, so if it did not release the mutex, then what happened? So it never released the mutex, then it go back to the top of the loop again. All right. When it go back to the top of the loop again, it tried to do another mutex acquire. All right, it tried to do another mutex acquire. So when it tried to do another mutex acquire, what happens? Okay, so this is where we must understand how the OS behaves. So as far as the OS is concerned, whenever you try to lock the mutex, you will try to lock the mutex. So in this case, I try to do a mutex lock over here. Okay, I try to do a mutex acquire. Now, is the mutex available? It's not available because it was already acquired. Okay, the mutex was already acquired earlier on. So when it tries to do another acquire, okay, it will fail. Okay, because the mutex is only 1 or 0. So it is originally 1. Now the current value is 0. So when you try to do another acquire, it will fail. So what will happen is at this point of time onwards, it will go to a block state. Okay, it does not matter that the green task was the one that actually acquired it earlier. Okay, all the OS looks at is when the task tries to do a mutex acquire, it will go ahead to observe what is the current status of the mutex. If it is available, it will allocate. Currently is considered not available because a task already acquired it. So the same task acquiring it again is still considered a second acquire. Okay, but it considered that it will go back into a block state. Okay, so when it goes to a block state, what happens? Then you can have a contact switch that happens. So when the contact switch happens, what is going to happen over here? So your currently your LED red is blocked because it tried to acquire mutex. Okay, it tried to acquire mutex, but it's not available. You go to a block state. So what happens? So even actually you will not have a contact switch at this point of time because your task 1 is already blocked. Okay, your LED task, red LED task is already blocked waiting for the mutex. So the only way that the block can transition to ready is if the mutex becomes available. But the mutex never becomes available because the green LED does another mutex acquire, which causes it to go to a block state. So what will happen is both of them will now indefinitely be blocked. So that is why you see that nothing happens. All right. So again, this is cases of using the mutex in a wrong way. Okay, in a wrong way. Okay, rightfully, like I said, the correct way is always you look at what are the shared resources. Okay, and then from the shared resources, you go ahead to decide. So from the shared resources, you lock before and then you release after. Okay, now let's look at this one more concept. Okay, now if you look at OS Mutex acquire, there is two things. One is OS Mutex, the other is this time. Okay, so this OS wait forever is actually a time. All right, the reason why we say that it's blocked forever is because we put the OS wait forever. Okay, so the OS wait forever means I will wait until I have allocated that resource. Okay, and in most cases that is what you want. Okay, in most cases that is what you want, because you want to make sure that because you know that I need this mutex to control this resource. So if I do not get it, then I should not control the resource. Okay, so you wait until it is available. Okay, but in some cases, okay, maybe you have a plan A and plan B, correct? That means you say that if I get the resource, I do this. If I don't get the resource, maybe I do something else. Okay, I do something else. So that is another alternative. Okay, so let me show you what I mean. So I'm going to comment off this LED red thread and we're going to uncomment this. So this is another LED red thread that I've written. So if you look at this LED red thread that I've written, the difference is when I call the mutex acquire, I don't say wait forever. I put a timeout of 0. Okay, that means what? That means I am not going to be waiting. I'm going to try to get the mutex. I'm going to try to get it. Okay, and if I get it, okay, my status, okay, will be OS okay. If it is not OS okay, means it is some error state. Okay, so all this you can look back at the online documentation later. All right, so whenever you call OS, okay, there is OS status return back. Okay, so I'm going to capture the status, so I will know whether it was successful or not. So if it was not successful, then I do something. If it is successful, I do something else. All right, so if you see down here, what I'm going to do is I'm going to try to acquire the mutex, and if I don't get the mutex, that means there's some error, I will control the blue LED. I'll just turn it on. Okay, but if I do acquire it, then I control the red LED. All right, so let me just run this code, okay, and I'll show you what happens. All right, so again, this is not I would say if you want to take this approach, you must think carefully of these two scenarios. That means what are the two things you want to, the if else things that you want to do if you get the mutex, if you don't get the mutex. So in most cases, like I told you, in most cases you will take the wait forever option. All right, but this is another option if you are very sure that you have a path to take if you do not get the mutex. Okay, so let me just show you what happens over here. Okay, so let me run it. So first is red, followed by okay, so it's not so clear, I think, on the screen. So basically, let me reset. So first it was red, and then there is actually a turquoise color, which is actually blue and green, and then it's only blue. All right, so basically what happens is the same scenario as before. All right, where the same thing is happening. So initially we see the red LED and then we see the green LED, but what happens is the moment the green LED gets delay, correct, and then you have a contact switch over here. Okay, so what happens is this acquire mutex does not block. Okay, it does not block anymore. So the red LED never gets blocked because of the acquire mutex, because the moment the acquire mutex is done and you fail the mutex, okay, because your green LED has it, you go ahead and light up the blue. Okay, so that is what happens. So what happens is you see the blue and the green both happening at the same time for a while. Okay, for 1 second, you see the blue and the green happening at the same time. And after 1 second, this one goes off. So only the blue remains. Okay, so subsequently, you can see that only the red LED task is running. Okay, and it just keeps the blue on. Whereas the green LED task is blocked. Okay, because it tries to acquire the mutex and it's wait forever. All right, so the red LED task in this case never gets a block state because you do not wait. Okay, you do not wait for the mutex. Okay, the code is written such that I will try to acquire the mutex and I will not wait. Okay, so if I get the mutex, I do this. If I don't get the mutex, I get this. Okay, that means there is some error in trying to acquire the mutex. Okay, so in this case, I do not block my red LED task at all. Okay, so again, you can see that even though the mutex concept is fairly easy and straightforward, but there are a lot of different ways you can sort of use it. Okay, and if you don't use it correctly, it can lead to a lot of unnecessary or funny behavior in your code. All right, so basically that is the things that you can try. Okay, so in the lab for this week. Okay, so try yourself, play around. Okay, with the mutex, the timeout, and see what happens. Okay, and then you will get a better understanding what's going on. All right, so this week's lab is on the priority and the mutex. The semaphore lab I will demonstrate next week. Okay, when we have done with the scheduling lecture. Okay, so the question is, if thread A locks the mutex, can thread B unlock the same mutex that thread A is locked? Okay, no. Okay, so whichever thread locks the mutex is the only one that can unlock the mutex. Okay, so if thread A has locked it, thread A has locked it, means thread A must unlock it. All right, so basically that's all I have for today. All right, if you have any questions, you can stay back and ask. If not, I will see you all in the lab.